All right. All right. Good morning, everyone. Thank you for joining this STMS seminar. We really do appreciate your continued engagement and encouragement for this seminar. Most of you know the format. We are going to have two talks, a long form and a short form, one for 30 minutes and one for 15 minutes. And we will continue having two events per month, at least through the summer of 2023. And then depending on the engagement, we'll decide the future. All right, so today we have two very interesting talks. And okay, our first talk is going to be from Professor Gaurav Arya. Professor Gaurav Arya is in the mechanical engineering and material science, biomedical engineering, and chemistry at Duke University. Before joining Duke in 2017, he was an assistant professor and then an associate professor of nanoengineering at UC San Diego. He started his academic career in IIT Bombay, where he got a BTech degree in chemical engineering in 1998. He went on to get a PhD degree with Ed Megan from University of Notre Dame in 2003 in chemical engineering. Then he did his postdoc research at Princeton with Thanos and in New York University with Tamar Schlick. He is published in many peer-reviewed articles and many prestigious journals. He's been interested in doing, using simulations to predict material properties and gain molecular level understanding of material behavior. He's studied polymers to, porous materials, and now we'll probably hear more about his DNA-related work. So Gaurav, we are very excited to have you here. Our second speaker is Ziqi Chen from University of Illinois Urbana-Champaign. She is a PhD student in chemical engineering from Baron Peters Group, and she got her bachelor's degree in chemical engineering from Syracuse in 2019 and has been working with Baron since. So we are very excited to have you here as well, and we look forward to both your talks. Gaurav, all yours.
Okay, I hope everyone sees the slides.
Yeah, we do.
All right. Well, thank you again for giving me this opportunity to share my work. Today, I'll be talking about my work on modeling of dynamics of polymers in a pore of a precessive upcycling catalyst. Okay, so the motivation of my work is the largely increasing amount of plastic waste. The plastic waste production now is over 3 million tons per year, and over half of them go to landfill. About a quarter has been incinerated, and only about 20% can be recycled. So there's an urgent need for a efficient way to recycle the polymer waste, since we produce them on a daily basis. Current recycling methods, including the mechanical recycling, which involves you collect them and grinding, then remelting them into flakes. But in this process, polymer loses its property and value. And then there's the incineration, but it also produces a ton of greenhouse gases, so it's also not ideal. So now moving on to the currently most promising recycle method is the polymer upcycling, which includes pyrolysis and catalytic reaction, which can further be broken down into hydrogenolysis, olefin metathesis, and other reactions. So we would prefer the catalytic reaction since it is efficient and selective, which are all essential to the recycling process. So the purpose of the polymer upcycling in total is just to produce value-added products rather than simply recycle it into a downgrade plastic. So in this way, we can convert plastic waste into liquid alkane olefins, alkyl aromatics, and further manufacture them into fuels, lubricants, feedstocks, and other products. So about the reaction that we will talk about today. So here's a figure that shows this core shell system that our collaborator developed. So we can see in the center here is the nanoparticle, And then outside of it is a shell with pores connecting to the particle surface. And there are the processive catalysts sitting at the bottom of the pore. So when you have polymers coming in from the bulk, it will reach the surface of the shell and then go into the pore. And when they reach the end, it will contact the processive catalyst and get cut into pieces on this point of contact. And remember, this is a processive catalyst. So it means the polymer will stay inside of the pore and keep getting cut until the reaction ends. And we are also assuming when the polymer is inside of the pore, it should have a diffusive reptation. So to put that into a simpler figure, it will be a one-dimensional pore, and you have polymers moving inward and outward of the pore. The total length of the pore should be is L, and the distance or the location of the polymer is defined as the distance from the end of the polymer to the end of the pore. So this distance here is Q. We have the initial location Q naught and the final location QT. So to observe how the polymer is moving inside of the pore, our experimental collaborator used the 2D NMR method, which basically is you record the polymer location at two different time instants, T1 and T2. Then you put them onto the two axes, and these peaks shows the polymer location and amount. For example, the peak 1 here will correspond to the portion of the polymer that stayed inside of the pore the whole time in both T1 and T2 and didn't leave the pore. And peak 3 and 4 corresponding to the portion that changed the location, either it moved outward or moved inward between T1 and T2. Then this large peak 2 here is the large chunk of polymer that stay outside of the pore the whole time and will be out of our consideration. So how do we interpret this NMR results, and how are they determined or related to polymer and pore properties? To do that, we will need to build a model to describe the polymer motion when it's inside of the pore. And the first thing for this model is a few assumptions. First, we assume when polymer is moving in the pore, it has a diffusive dynamic. Secondly, we assume the polymer will have a linear free energy linear to its location, the location Q that we mentioned before. That is to say, there is a constant force or like free energy force pulling this tail here for it to stay inside of the pore. So it would prefer to stay inside to finish the processive reaction. Finally, we assume the diffusivity of the polymer when it's in there should be independent of its location. Wherever it is, it has the same diffusivity. So with these three assumptions, we set up a Smolachowski equation to describe the polymer motion. Why using this long equation instead of a fixed law? Because not only we have the diffusive dynamic, we also have this linear free energy profile, a constant external force that is pulling the polymer. So it can be described by the Smolachowski equation. We also have the no flux boundary condition, which means the polymer never fully leaves the pore. It can also never penetrates the end of the pore. So now the non-dimensionalization. We non-dimensionalize all the variable by 1 kBt. So there will be the non-dimensional length and time. Also, the previous equation has the simpler form with the same boundary condition, no flux boundary condition. With the non-dimensional form of the equation, we can already make a few predictions. First, if we take the non-dimensional time to 1, then we get the settling time to be expressed this way. And if we take the time to infinity, we will get the equilibrium solution, which is a exponential decay. But having these predictions is still not sufficient for us to understand how the diffusivity and free energy is affecting the system independently, like to understand how the polymer motion is in the pore. And to do that, we will need to fully solve this partial differential equation. And we refer to the Mason-Weaver theory in 1924, where they study the settling of small particles in fluids. These particles has both gravitational drift and Brownian movement with a no flux boundary condition, which bring us to the exact the same setup as our problem. So we adapt their method for solving the equation and build our own solution for a delta initial condition in the form of a Green's function. So we can see here, you start with this peak at x equal to 1, and then evolve into the exponential decay as we predicted before. So now with the Green's function, we have the solution for all initial condition using superposition. Basically, you take the Green's function and you multiply that by the initial condition, and then you integrate it over all the points. So it's like on all the points you have the solution for a point source, and you integrate it over the whole axis. Then you have the full solution for the equation. So here shows the solution for a step initial condition. You start with a step from 0 to 1 and grow into the equilibrium solution. Now, with this full set of solution, we can go back to the NMR data and use this solution to interpret the NMR peaks. But how do we compute the peak intensities? We will need to consider, take peak 1 as example. We take the initial equilibrium condition, then we multiply by the Green's function as shown before. Then it's the minimum of whichever of the T1 and T2. So whichever is smaller in this case, since the polymer is moving outward, so at the final location will be the smaller one. So it will be the L minus QT. L is the total length of the pore, and QT is the final location. So L minus QT represents the peak 1, that is the portion that stay inside of the pore the whole time. So it will be the initial equilibrium solution and the Green's function, then the portion of the polymer. And for peaks 3 and 4, similar logic. We have the initial equilibrium solution in condition and the Green's function, then the differences between the final and initial location, and take the absolute value. So this 1/2 here is to correct for the fact that you can either have QT larger than Q0 or Q0 larger than QT. Like put that on a XY axis, it will be either the upper triangle or the lower triangle. So this is what the 1/2 is correct for. Is for this absolute value here. Now with this integrants, we just need to integrate it over all the starting points and all the ending points. We can acquire the peak intensity. Since the cross peak intensity, so the portion of the polymer that is changing location in the process is what we are focusing on. And we're also normalizing that peak using peak 1. But here we are approximating peak 1 using the total pore length L, because from experimental data, we know that about 70 to 80% of the pore is always occupied. So we can just approximate it by the whole length. After integrating this equation, we get a closed form expression for the peak intensity. And we fit that curve to the NMR data under 3 different temperatures. This is what we get. From this fitting, we are able to extract 2 parameters we mentioned before. First is the diffusivity of the polymer. And then there's the free energy per nanometer of the polymer. We also compute the per segment free energy, which is assuming there's 8.2 CH2 segments per nanometer. And so it just divided by 8.2. These error analyses are performed using the bootstrapping method. We further analyze these data. First, we extract the enthalpy and entropy part from the free energy using the Gibbs-Helmholtz equation. And secondly, we assume the diffusivity follow a Arrhenius law and use the Arrhenius law to extract a activation energy for the process. The error analysis here and for the previous enthalpy and entropy part are performed using the ANOVA analysis. So here's a quick conclusion. We built a model for polymer dynamic in a dead-end pore. Then we fit the model to the NMR data at different temperature and extract the diffusivity and free energy at different temperature. There's the references, and I would like to thank all the funding sources and everyone in Peter's group for supporting me the whole time. And now to the question. Thank you.
All right. Thank you, Ziqiu, for the wonderful talk. We have time for questions. I lost my chat. Go ahead.
Can you go back to the slide where you showed the F? So you're saying basically this force varies linearly. Are you accounting for the entropy of the polymer lost when it goes in? And does that scale linearly with the length? There's a lot of polymer that's kind of hanging outside. And as you put more and more of the polymer inside, you lose the entropy of those, like the conformational entropy of the polymer. Is that kind of included in the model, or do you just only include enthalpic sort of, or anentropic due to just adsorption of the polymer inside? Maybe I missed it.
So thank you for the question. The assumption here is that with a really long entangled polymer, you have like a short tail inserting into the pore. So, and it's like really moving, like the length of the pore is typically like 100, 110 nanometer. And so it's relatively like really short comparing to the whole like large polymer. So it's like this whole chunk that is out there will almost not experience any change. Well, in this figure, you might think there's a significant portion going in, but actually there's a really huge part here that don't change or pulling it during the whole process. All the free energy here, free energy that we show here is just to encounter for this little tail that's inside of the pore, like the interaction between the polymer and the pore inner surface.
What if the polymer was not entangled in an entangled state, but it was kind of in a free solution, kind of in a solution where it's expanded, swollen, kind of good solvent conditions? Do you think that assumption would still hold?
Yeah, well, if we have to take into account the effect of the portion that is outside of the pore, then definitely this will be set up in a different way, because here we are assuming we are just cutting the portion outside of it, just out of our consideration, that we only care about this little part that's inside of the pore.
I see. Nice work. Yeah.
Thank you.
All right. Do we have any other questions? Okay, I can ask a very naive question. In this model, are you assuming that the pore width is almost equal to sort of the size of the polymer bead, such that it can't have any any motion within the pore itself beyond just going in one dimension?
Yes, that's a great question. We definitely thought about that, and I think I marked somewhere about the Kuhn length of this of the polymer. So the pore size should be fit to a size that it will allow some folding at the end, because that's how the reaction is happening, like shown here. It has to fold a little bit on the tail for it to be able to cut, but for the middle part, it wouldn't be able to for the polymer to like fold multiple times in the middle, because I think the pore size is like 2 nanometer. It's like slightly able for you to wiggle a little bit, and like for the small pieces to wiggle out, but it wouldn't be able for the long chain to tangle too much in the middle. So it should almost be a linear, and that's also what we see from the NMR peaks, to show that it should have a configuration of mostly linear.
Okay, that's very cool. Cool.
Thank you.
Gaurav, do you still have a question, or is this from you before?
No, I have a question. So
Okay.
have you also looked at the energy barrier for the polymer getting into the pore itself? Have you looked at that problem also? Because it's very difficult, right, for this guy to find the pore and then actually try to, because there should be a huge kind of a surface entry barrier, right? Or there isn't. Actually,
the assumption here is the polymer melt exists a excess amount of polymer waiting to get cut, and you have like a few of these
so it's actually favorable sometimes in some way.
Yes,
because
like
the melt actually likes it if the polymer actually goes into the
it always favors the polymer.
It actually almost pushes it in.
Yes.
I see. Okay, that's a good point. Yeah. Okay, thanks.
No problem.
All right, I don't see any more questions. So let's thank Ziqiu again, as well as Gaurav. Thank you very much for the wonderful talks.
Thank you.
And with that, we end our event for the day, but you're welcome to hang out and catch up with your friends and colleagues if you like.
Thank Gaurav, thank Ziqui, very beautiful talks.
Yeah, I'll hang around.